Hello, and welcome to Lesson 7 for Foundations for Algebra Unit 1A. So today's objective is that scholars will compare functions written in different representations. We've talked about the different ways that functions can be represented, and now we're going to look at actually comparing two that are written differently. So our first question is, how can functions be represented? We've looked at this before. So let's look at this problem. You can highlight along if you want to. 3 cars are traveling to the same campground along the same route. The cars began at the same place, but at different times. Car A began the trip at noon, and cars B and C began the trip at different times before noon. The miles traveled by cars A, B, and C are represented respectively by the following graph, table, and equation. So the information we have here is car A began the trip at noon. Cars B and C began the trip at different times before noon. So now let's look at the information we have for each of these. So here we have the distance that car A travels. This, of course, is a graph. So car A, we have a graph. Car B, right here, is a table. So car B, wrong color. Car B is a table. And then here at the bottom we have car C. I'm messing up the colors today, sorry guys. Car C. And here we have an equation. D is our total distance and T is the time. So I have an equation, I have a graph, and I have a table. And the question we're being asked to answer is, at what time, if ever, will car A pass each of the other cars? And then we have to describe any assumptions. Those are things that we sort of make a guess at without having actual pre-assumptions you make to justify your answer. So how can we do this? Well, the simplest way is to put all the information in one format. They gave us this information for car B. That's the same information that was on the table on the previous slide. But we can fill in that information for car A from the table and for car C from the equation. So let's look at filling that in. Hold on, so let me change that color. Make it a little bit easier. So car C will do from the equation. So car A, I want to know at 1 hour since noon, what is the distance for car A? So I'm going to come down here to my graph. At 1 hour, it looks like he's probably like maybe 60 miles. He's more than 50, but not to halfway point 60. So I'm going to say he was 60 miles. So I'm going to say car A is 60 miles. Remember, these are sort of approximate, right? Well, he definitely hasn't passed car B yet because car B was 110 miles. So now let's go for where he is at hour 2. So hour 2, again, we're going to come over here, time afternoon is 2. Come up here and looks like he's more than halfway between 100 and 150. I'd say maybe he's 140. 140 miles. So maybe the other one was 70. I don't know. Like I said, we're just going to keep going with it. And then we're going to do the same thing at hour 3. May come down here to 3, go up. It's a little over 200, so let's say 210. At hour 4, again, I just could come up from 4. And it looks like that's about 275. And then at hour 5, and do the same thing. It looks like he hit almost exactly. So this one looks like it's almost exactly hour 5, exactly at 350. So that one is 350. Again, we're making approximations from our graph. Well, now let's look at car C. Car C, we've been given an equation. So remember that the hours past noon is our time. So I want to find out what the distance is when the hours past noon are 1. So I want the distance when it's 68 times 1 plus 20. Well, 68 times 1 just gives me 68, plus 20 is 88. Then, I'm going to use my eraser here to erase the 1. Now to find out 2, I'm just going to really times 2. So 68 times 2 gives me 136 plus 20 will give me 156. And we're going to do the same thing for at 3. Sorry. And my eraser. Erase that. Erase the 2 and turn that into a 3. So 68 times 3 give me 194 plus 20 makes it 214. And then again I'm going to substitute the 3 for a 4. So 4 times 68 plus 20 gives me 282. No, 292. Sorry, 292. And then another 68 gives me 360. Okay? So now that I've filled in this table, let's look at it, and I've given another slide where I filled them all in. And this one, you see my numbers are a little bit differently, that's fine. I looked at it a little differently each time. But now let's look at car C stayed the same. So the question is, at what time, if ever, will car A pass the other cars? Remember, they're all starting at the same point. They're all ending at the same point. So I'm looking at a point where car A passes one of the other cars. So if we look at 1 hour, at 1 hour, car B is definitely the furthest at 110 miles at 1 hour after noon. Remember, cars B and C started before noon. At 2 hours, has car A passed? Well, it's only at 150 miles, and they're at 175 and 156. So it still hasn't passed. What about at hour 3? At hour 3, I'm at 225. I still haven't passed car B, but I've passed car C. So I can write car A passes car C. Within 3 hours. Because it happened obviously before that if I'm past them. But I don't know exactly where. And then we're going to check the same thing for so at hour 4, we are still past car C, but we haven't passed car B. We're still 5 miles behind them. At hour 5, I've now passed car B. So then I'm just going to write car A passes car B within 5 hours. So what does that mean? Which one's traveling the fastest? We know car A started last. But which car is traveling the fastest? If it passes cars B and car C, then car A must be traveling the fastest. Okay, so go ahead and try your work, and I will see you in class.